Here's something that's going to sound absurd until I explain the science behind it. You've just pulled into the gas station. You're about to start pumping fuel into your vehicle. But in the 60 seconds before you even touch that pump handle, you may have already initiated a sequence of events that will cost you hundreds, possibly thousands of dollars in repairs over the next 12 months. I'm not talking about what you do during fueling. I'm talking about what you fail to do in those critical moments before the first drop of gasoline enters your tank. This isn't about minor convenience tips. This is about understanding the precise mechanical and chemical vulnerabilities that exist in the window between parking your vehicle and engaging the fuel nozzle. I've been diagnosing fuel system failures for over 2 decades, and the pattern is undeniable. The majority of expensive fuel-related repairs trace back to a handful of preventable mistakes that happen before fueling even begins. We're going to dissect each one with the kind of technical depth that separates professional mechanics from weekend hobbyists. By the time we're finished, you'll understand your fuel system at a level that 90% of drivers never reach, and you'll possess the exact protocols to protect your investment. But first, I need to establish something with you. Are you genuinely ready to change your habits based on engineering facts, not marketing myths? If the answer is yes, then demonstrate that commitment right now. Hit that subscribe button and turn on notifications. This channel exists because people like you want the unvarnished technical truth about their vehicles, and your subscription is what funds the hundreds of hours I invest in this research. Now, tell me in the comments, what city or region are you from? I'm curious about the geographic distribution of our community, and it helps me tailor future content to regional fuel and climate challenges. Drop your location below, hit that like button, and let's proceed. The mistake I'm about to describe is invisible to most drivers because it happens internally, within the fuel tank itself, triggered by your driving behavior in the final mile before you reach the station. The error is this: approaching the gas station with your fuel gauge in the red zone, having run the tank to near empty, then immediately refueling. This seems innocuous. You're simply maximizing the interval between fill-ups, but you're actually executing a destructive cycle that systematically damages one of your vehicle's most expensive and critical components, the electric fuel pump. To understand why, we need to establish the operational physics of this pump. The fuel pump is an electric motor coupled to an impeller assembly. It lives inside your fuel tank, fully submerged when the tank has adequate fuel. This submersion is not a design choice for waterproofing. It's a thermal management necessity. Electric motors convert electrical energy into mechanical work, but this process is inefficient. A significant percentage of the input energy becomes waste heat. In a traditional air-cooled motor, a fan or external airflow dissipates this heat. Your fuel pump has no such luxury. It relies entirely on the surrounding liquid gasoline to absorb and carry away thermal energy. Gasoline is an excellent heat sink for this application because it has a high specific heat capacity and is constantly being circulated through the pump during operation. When you run your tank down to the reserve level, several catastrophic thermal conditions begin to converge. First, the pump becomes partially exposed to air. Air has roughly 1,000 times lower thermal conductivity than liquid gasoline. The sections of the pump motor that are no longer submerged begin to retain heat. The internal windings, brushes, and armature experience elevated temperatures beyond their design parameters. Second, as the fuel level drops, the pump begins to cavitate. It starts ingesting a mixture of fuel vapor and air instead of pure liquid. This reduces cooling efficiency further and forces the pump to work harder, drawing more current to maintain system pressure. Higher current equals more resistive heating in the windings. You've created a vicious thermal spiral. The metallurgical consequences are precise and irreversible. The copper windings in the motor are insulated with a thin polymer coating. This insulation has a maximum continuous operating temperature, typically around 130 to 150 degrees Celsius. When you exceed this threshold repeatedly, the insulation begins to degrade. It becomes brittle, cracks, and eventually fails, allowing adjacent windings to short circuit. The carbon brushes that ride on the commutator experience experience accelerated wear at high temperatures. Their spring tension degrades, contact resistance increases, and arcing intensifies. The pump's bearing surfaces, often simple bronze bushings lubricated by the fuel itself, run dry when exposed to air and vapor. Metal-on-metal contact generates friction, heat, and microscopic welding, leading to seizure. The failure mode is often sudden and total. You'll be driving normally, and the engine will begin to stumble, lose power, and eventually stall as fuel pressure drops to zero. The pump has seized or the windings have opened. You're stranded. The repair is not trivial. Accessing the fuel pump requires dropping the entire fuel tank from the vehicle, or, in some designs, removing the rear seat and cutting through an access panel. Labor alone is 2 to 4 hours at shop rates. The pump assembly itself can range from $300 to $800 depending on the vehicle. You're looking at a minimum bill of $700, often exceeding $1,200. The preventive protocol is elegantly simple and transforms this abusive cycle into a protective one. Establish a firm personal rule. Refuel when your gauge reaches the 1/4 tank mark, not the low fuel warning light, not the reserve zone. 1/4. This single discipline guarantees the pump remains fully submerged in its cooling medium during all operating conditions. It ensures you're drawing fuel from the cleaner, upper portion of the tank away from settled sediment. In cold climates, it prevents fuel line freeze by minimizing the air volume available for condensation. In hot climates, it prevents vapor lock. This is not a suggestion. This is a non-negotiable maintenance protocol if you want your fuel pump to reach its design life of 150,000 miles or more instead of failing prematurely at 70 or 80,000. The second critical mistake occurs in the transition moment between driving and parking at the pump. The error is this. You pull into the station, you've been driving aggressively or at highway speeds, and you immediately shut off the engine and begin fueling within seconds. You've just trapped superheated fuel in a closed system at the worst possible moment, creating conditions for vapor lock, fuel system pressure spikes, and premature wear on fuel line components. Let me explain the thermodynamics at work here. When your engine is under load, particularly during highway cruising or acceleration, the fuel system is operating at its maximum flow rate. The fuel pump is running continuously, circulating fuel from the tank through the fuel lines into the fuel rail at the engine, and then returning excess fuel back to the tank via the return line in a return-type system, or simply maintaining high pressure in a returnless system. This circulation generates significant frictional heat. The fuel itself absorbs heat from the engine bay as it passes through lines routed near the exhaust manifold, turbocharger, or cylinder head. By the time the engine shuts off after spirited driving, the fuel in the lines and rail can be 20 to 40 degrees Celsius above ambient temperature. The moment you turn the key off, circulation stops. The fuel pump stops running. The fuel that was moving, dissipating heat, is now static. In the engine bay, this trapped fuel continues to absorb radiant heat from the still glowing exhaust components and the cooling engine block. Because it's no longer circulating, it has no mechanism to shed this heat. Temperature rises, gasoline is volatile, it has a low boiling point compared to many liquids. At elevated temperatures, especially in a low-pressure environment, it begins to vaporize. This is called heat soak. In a fuel line, vapor formation is a problem. Fuel injectors require liquid fuel at a specific pressure. Vapor is compressible. Liquid is not. If vapor bubbles form in the fuel rail or lines before your next start, the fuel pump must work harder to repressurize the system. In extreme cases, the engine may experience hard starting, rough running, or even a no-start condition because the injectors are receiving vapor instead of atomizable liquid. This is classic vapor lock. It's rare in modern fuel-injected systems compared to carbureted engines, but it still occurs, particularly in hot climates or after aggressive driving. But there's a more insidious issue related to fueling during this heat soak period. When you open the fuel tank immediately after shutting down a hot engine, You're introducing ambient temperature fuel into a system where the existing fuel is already heat-saturated. The differential can cause localized boiling at mixing points. More critically, you're opening the sealed tank at a moment when vapor pressure inside is elevated due to heat soak. This can cause an overly rich vapor cloud at the filler neck, increasing the evaporative emission losses and, in rare cases, creating a flash fire hazard if an ignition source is present. The professional protocol is to institute a mandatory cool-down period. After parking at the pump, wait a minimum of 2 to 3 minutes before opening the fuel door. I know this sounds excessive in our instant gratification culture, but the physics doesn't care about your schedule. During this wait, several beneficial processes occur. The fuel lines begin to equalize temperature with the ambient environment. Any vapor bubbles that have formed begin to condense back into liquid as pressure and temperature stabilize. The engine bay heat dissipates slightly, reducing the thermal load on the static fuel. When you finally open the tank, you're doing so in a thermally stable state, not during the chaotic peak of heat soak. This wait costs you nothing but patience, yet it protects your fuel system from thermal stress, prevents hard start conditions, and reduces evaporative emissions. It's a mark of someone who understands that machines have thermal time constants that must be respected. This is how professionals operate. This is how you extend component life. Now, let's address a behavior that seems prudent on the surface but is actually setting you up for contamination and fuel system degradation. The mistake is this: you arrive at a gas station. You notice the price is attractive, but your tank is still 3/4 full. You think, I'll top it off now to lock in this price and avoid a stop later in the week. You proceed to add only 2 or 3 gallons to an already mostly full tank. You've just violated a critical principle of fuel tank chemistry and sediment management. Every fuel tank, regardless of how well maintained, accumulates a certain amount of sediment over time. This sediment is a mixture of several contaminants. There's rust particulate from the tank's interior walls, especially in older vehicles with steel tanks. There's silica and dust that entered during previous refuelings through imperfect pump seals. There's degraded fuel from previous fill-ups, gum, and varnish deposits that have precipitated out of solution. There may even be microbial growth if water contamination has occurred. All of this material, being denser than gasoline, settles to the lowest point in the tank over time. It forms a concentrated sludge layer at the very bottom. Your fuel pump's intake is equipped with a coarse pre-filter, often called a sock or strainer. This sock is positioned slightly above the absolute bottom of the tank to avoid drawing directly from this sediment layer under normal conditions. When your tank is half full or more, the intake is well above the sludge zone, drawing from the cleaner upper volume of fuel. This is the ideal operating state. When you perform frequent small top-off fills, you disrupt this beneficial stratification in a subtle but damaging way. Each time you add fuel, you create turbulence in the tank. The incoming fuel splashes, swirls, and mixes with the existing fuel. When the tank is nearly full, this turbulence is constrained to a small vertical space near the top. It doesn't reach down to disturb the sediment layer at the bottom. But when you're topping off 3/4 of a tank, you're adding fuel that must displace the existing volume. This creates circulation currents throughout the tank. These currents can lift fine sediment from the bottom and suspend it throughout the fuel column. Now, your next drive draws this suspended contamination directly into the fuel pump. The sock filter captures some, but it has a finite capacity. Over time, repeated top-offs mean repeated resuspension of sediment. The sock clogs faster than it would under a normal refueling pattern. A clogged sock increases the fuel pump's workload, leading back to the thermal stress and premature failure we discussed earlier. Worse, if the sediment is fine enough, it can pass through the sock and reach the main fuel filter. It accelerates filter clogging. In the worst case, it reaches the fuel injectors, causing partial blockages that degrade spray patterns, reduce fuel economy, and trigger lean condition fault codes. Have you ever wondered why some professional fleet operators and manufacturers recommend waiting until the tank is at least half empty before refueling? This is precisely why. They want to minimize the number of refueling events and maximize the volume added per event. Fewer refueling events mean less total turbulence over the vehicle's lifetime. Larger fuel additions allow the sediment disturbed by the incoming fuel to settle back down more completely before the next disturbance. The corrective strategy is to adopt a minimum threshold for refueling. Do not add fuel unless your tank is at or below the half-full mark. Ideally, refuel when you're between 1/4 and 1/3 tank remaining. This ensures that each refueling event adds a significant volume of fresh fuel, diluting any contaminants and allowing a longer settling period between fills. It keeps your fuel pump drawing from the clean zone. It maximizes filter life. It's a discipline that costs you nothing in convenience but saves you significantly in maintenance and repair over the vehicle's lifespan. Your fuel system will thank you with quiet, reliable operation year after year. We're at a critical juncture in this discussion, and I need to gauge your engagement. Are you absorbing this information, or are you passively listening while scrolling? If you're genuinely committed to mastering these principles, prove it with action. Drop a comment right now telling me which of these mistakes you've been making. Honesty is valuable here because it helps others realize they're not alone. Are you guilty of running your tank to empty? Do you top off constantly? Are you the person who shuts down and immediately starts fueling? Write it in the comments. And if you haven't yet liked this video, do it now. That simple click tells the algorithm to share this knowledge with more people who need it. Your engagement has direct consequences for the reach of this technical education. Let's continue. The next mistake is one of spatial awareness and vehicle positioning, and it has direct consequences for fuel system integrity and even personal safety. The error is this: you pull into a gas station on a steep incline or with your vehicle severely tilted, and you proceed to fuel without considering the orientation of your fuel tank relative to gravity. You've just created conditions for incomplete filling, air entrapment, or, in certain vehicles, a dangerous overflow scenario. Modern fuel tanks are complex molded structures designed to fit within the constrained space of a vehicle's underbody. They are not simple rectangular containers. They have irregular shapes with multiple lobes, baffles, and internal partitions. These baffles serve to prevent fuel slosh during cornering and braking, which is important for vehicle stability and pump pickup consistency. The filler neck connects to the tank at a specific location, and the tank's vent system, which allows air to escape as fuel enters, has a vent tube or valve positioned at what the engineers determined would be the tank's highest point when the vehicle is level. When you park on a significant incline with the fuel door positioned uphill, you're inverting this design assumption. The vent, which should be at the top, may now be at a mid-level or even low point relative to the tilted fuel column. As you pump fuel, the liquid rises in the filler neck and begins filling the tank. Air inside the tank needs to escape, but because the vent is no longer at the highest point, a pocket of air becomes trapped at the new, elevated section of the tilted tank. This trapped air cannot easily escape through the vent because liquid fuel or the tank's geometry is blocking the path. The trapped air creates back pressure. The automatic shutoff mechanism in the fuel pump nozzle senses this back pressure and interprets it as the tank being full. The nozzle clicks off, even though the tank may have several gallons of unfilled capacity. You're paying for a fill-up, but receiving a short fill. Over time and many refuelings, this adds up to real money. More critically, the trapped air creates an inconsistent fuel level reading. Your fuel gauge may show less than full immediately after refueling because the float is reading the actual liquid level, not the total apparent capacity. In some vehicles, particularly older models or those with certain vent system designs, the opposite problem can occur. If the filler neck is positioned downhill and the vent is uphill, fuel can backflow into the vent system or even overflow from the filler neck onto the ground or the side of your vehicle. This is not just wasteful and messy, it's a fire hazard. Spilled gasoline on a hot exhaust component or pavement can ignite if a spark source is introduced. The solution requires deliberate vehicle positioning. Before you pull up to the pump, take 3 seconds to assess the terrain. Look at the slope of the concrete pad. Notice if the station is built on a hillside. Your goal is to position your vehicle as level as possible. If the station has multiple pumps, choose the one on the most level ground. If that's not possible, and you must use a sloped spot, try to position your vehicle so the fuel door side is either level or slightly downhill relative to the opposite side. This uses gravity to assist both fuel flow and air venting. In practical terms, if your fuel door is on the right side and the ground slopes left to right, you're in the optimal position. The fuel flows naturally into the tank and air vents easily from the highest point. If you must park with the fuel door uphill, expect the pump to click off early. You may need to wait a few seconds and try again, allowing the trapped air to slowly find its way out, but understand you're fighting the physics of the situation. This attention to positioning is a small detail that demonstrates a comprehensive understanding of how fluid systems operate under real-world conditions. The next error is one of procedure, specifically related to the fuel filler cap and the integrity of your vehicle's evaporative emission control system. The mistake is this: you've finished fueling, you replace the gas cap, but you don't tighten it properly, or you cross-thread it, or you ignore a damaged cap because it's been leaking for weeks and you haven't gotten around to replacing it. This negligence has cascading consequences that will cost you far more than the $15 replacement cap you're avoiding. The fuel filler cap is not a simple plug. It is a precision-engineered sealing component and an integral part of the evap system. This system is designed to prevent raw gasoline vapors from escaping into the atmosphere. It's a legal requirement for emissions compliance and is heavily monitored by your vehicle's onboard diagnostics. The cap itself contains a two-stage pressure relief valve. This valve allows the tank to breathe slightly during normal thermal expansion and contraction of the fuel due to temperature changes, but it maintains a seal during the diagnostic tests the vehicle's computer performs. The OBD2 system, mandated on all vehicles since 1996, includes a specific test protocol for EVAP system integrity. The engine control unit will command the purge valve closed and the vent valve closed, creating a sealed system. It then monitors the fuel tank pressure sensor to see if the system can hold a vacuum or slight positive pressure. If the system cannot hold pressure, indicating a leak, the ECU stores a diagnostic trouble code and illuminates the check engine light. The threshold for detection is incredibly sensitive, often calibrated to detect a leak as small as 0.020 inches in diameter, roughly the size of a pinhole. A loose, damaged, or missing gas cap is the single most common cause of EVAP system fault codes. It's such a prevalent issue that many auto parts stores offer free code scanning and will check your gas cap first. But beyond the diagnostic annoyance and the check engine light preventing you from passing emissions inspection, there are tangible losses. Every time your cap leaks, you're venting raw gasoline vapors to the atmosphere. These are hydrocarbons you paid for, now escaping as gas. In hot weather, a faulty cap can allow significant evaporative losses, potentially costing you a measurable fraction of a gallon over weeks. That's your money evaporating. Moreover, a compromised seal allows moisture and contaminants to enter the fuel system through the filler neck. Dust can enter, eventually making its way to the tank and fuel filter. More critically, humid air can enter, leading to condensation inside the tank, especially during temperature swings. Water in the fuel tank promotes corrosion of the tank itself and can lead to phase separation in ethanol-blended fuels, creating a water-ethanol layer at the bottom that the engine cannot combust. The correct protocol is non-negotiable precision. After fueling, thread the cap back onto the filler neck carefully, ensuring it engages smoothly without resistance. If you feel resistance or the cap doesn't turn smoothly, stop, remove it, and try again. You may have cross-threaded it, which will damage the threads on the filler neck, an expensive repair. Once engaged properly, tighten the cap until you hear at least 3 distinct clicks. Many caps have a ratcheting mechanism that produces this clicking sound to indicate proper sealing torque. Do not just stop at 1 click or when it feels snug, 3 clicks minimum. As a preventative maintenance item, inspect your gas cap every time you fuel. Look at the rubber gasket on the underside of the cap. It should be pliable, smooth, and complete with no cracks, tears, or permanent deformation. If it feels hard, brittle, or shows any damage, replace the cap immediately. A quality OEM or OEM equivalent gas cap costs between $15 and $30. This is a trivial expense compared to the hundreds you'll spend on diagnostic fees and potential repairs if you ignore it. Replace the cap every 5 years or 60,000 miles as a preventative measure, even if it looks fine. The rubber deteriorates over time from heat, ozone, and fuel exposure. This simple discipline prevents a huge category of check engine light issues and maintains your fuel system's integrity. Another mistake rooted in misunderstanding the chemical properties of modern gasoline is this. You arrive at a station and you select a fuel grade based on price, marketing, or a vague notion of quality without consulting your vehicle's specific engineering requirements. You're either wasting money on unnecessary octane or, worse, damaging your engine with insufficient octane. Both scenarios represent a failure to understand what octane rating actually means and how it relates to your engine's design. Octane rating is not a measure of fuel quality, energy content, or cleaning power. It is exclusively a measure of the fuel's resistance to knocking, which is uncontrolled detonation. Your engine operates on a 4-stroke cycle: intake, compression, power, and exhaust. During the compression stroke, the piston moves upward, compressing the air-fuel mixture in the cylinder. This compression raises both pressure and temperature. In a high-performance or turbocharged engine, compression ratios can be very high, or boost pressure can elevate cylinder pressure significantly beyond atmospheric. Under these extreme conditions, the air-fuel mixture can reach a temperature and pressure point where it spontaneously ignites before the spark plug fires. This is pre-ignition or detonation, commonly called knocking or pinging. Detonation is catastrophic. It creates an uncontrolled pressure spike and flame front that collides with the piston crown violently. The characteristic metallic pinging sound you hear is the shock wave bouncing inside the cylinder. Repeated detonation will damage piston rings, crack piston crowns, erode the head gasket, and destroy bearings. To prevent this, high-compression engines require fuel that is more resistant to spontaneous ignition under pressure and heat. This resistance is quantified as the octane rating. Higher octane fuel can withstand higher compression without detonating. If your vehicle's engine is designed for regular unleaded, which is typically 87 octane, it has a compression ratio and ignition timing calibrated for that fuel. Using 91 or 93 octane provides zero performance benefit. The engine's computer is not programmed to advance ignition timing to take advantage of the higher knock resistance, because the engine doesn't need it. You're paying a premium, often 20 to 40 cents more per gallon, for a chemical property your engine cannot utilize. It's pure waste. Conversely, if your vehicle's manual specifies premium fuel required, which is usually 91 octane or higher, the engine has a high compression ratio or forced induction that demands it. If you use 87 octane, the knock sensors in the engine will detect the onset of detonation. The ECU will respond by retarding ignition timing, pulling the spark event later in the compression cycle to reduce peak cylinder pressure and temperature. This prevents immediate engine damage, which is good, but it comes at a severe cost. Retarded timing reduces power output, sometimes by 10 to 15%. It reduces fuel efficiency significantly because the combustion event is no longer optimized. The engine may run richer, increasing fuel consumption and carbon buildup. You're saving 10 cents per gallon but using 20% more fuel and driving a car that performs like it's sick. Over time, the carbon buildup can foul spark plugs, clog intake valves, and reduce engine lifespan. The ethanol content adds another variable. Most pump gasoline in the United States is E10, meaning up to 10% ethanol by volume. Modern engines are designed and calibrated for this. However, some stations offer E15 or even E85, which is 51 to 85% ethanol. Ethanol has different combustion characteristics, lower energy density, and different solvent properties than gasoline. Using E15 in a vehicle not approved for it can accelerate wear on fuel system components not designed for higher ethanol concentrations, such as certain rubber seals and fuel pump materials. Using E85 in a non-flex fuel vehicle will cause severe drivability problems, potential engine damage, and will likely result in a no-start or stalling condition. The only authoritative source for your vehicle's fuel requirements is the owner's manual and the label inside the fuel door. It will explicitly state whether the vehicle requires premium fuel or if regular is acceptable. adjustable. Some vehicles will say premium is recommended, which means the engine is designed for it and will perform best on it, but it can tolerate regular with timing retardation if necessary. For maximum performance, longevity, and efficiency, use the recommended fuel grade consistently. Do not attempt to alternate tanks or blend grades. The ECU's adaptive learning works best with consistent fuel. This is non-negotiable engineering guidance. Respected. We've reached the halfway point of this technical breakdown, and I need to assess your retention and application intent. If this information is genuinely changing how you think about your vehicle, then engage with it actively. Scroll down right now and tell me which fuel grade your vehicle requires and whether you've been using the correct one. Have you been wasting money on premium when your car needs regular, or have you been cheating your turbocharged engine with 87 when it demands 91? Write it out. This act of self-reporting solidifies your learning. And if this level of detail is valuable to you, make sure you've subscribed and turned on notifications. We have an entire library of technical deep dives on this channel, covering everything from transmission fluid to brake system hydraulics. Your subscription ensures you don't miss the next critical piece of knowledge. Let's move forward. The seventh mistake involves a failure to understand the relationship between ambient temperature, fuel volatility, and the time of day you choose to refuel. The error is this: you consistently fuel your vehicle during the hottest part of the day, mid-afternoon in summer, without recognizing that you're receiving measurably less energy per dollar spent due to thermal expansion of gasoline. Gasoline is a liquid hydrocarbon mixture, and like all liquids, it expands when heated and contracts when cooled. The coefficient of thermal expansion for gasoline is approximately 0.95 per degree Celsius. This means that for every degree Celsius increase in temperature, a given volume of gasoline expands by roughly 0.095%. That might sound trivial, but let's calculate the real-world impact. On a hot summer day, underground storage tank temperatures can range from 15 to 25 degrees Celsius, depending on depth and ground insulation. If the gasoline is dispensed on a day when the ambient temperature is 35 degrees Celsius and the fuel has been sitting in above-ground dispensing lines exposed to sunlight, the fuel temperature at the nozzle can easily be 30 to 35 degrees Celsius. Let's compare fueling at two different times. Early morning, the gasoline temperature is 15 degrees Celsius. You pump 50 liters. That 50 liters contains a certain mass of hydrocarbons, which is what provides the energy for combustion. Now, same station, same pump, mid-afternoon. The fuel temperature is 30 degrees Celsius. 15-degree difference. That same dispenser will still show 50 liters on the meter, but due to thermal expansion, those 50 liters contain less mass of actual hydrocarbons. The difference is approximately 0.095% per degree times 15 degrees, which equals roughly 1.4% less mass. On a 50-liter fill-up, you're receiving about 7 liters less actual fuel energy, even though you're paying for 50 liters. Over a year, if you fuel exclusively in the afternoon heat versus the cool morning, this can add up to several hundred kilometers of lost range, costing you real money. The fuel dispensed is measured volumetrically by the pump's meter, not by mass or energy content. You pay by the liter or gallon, but you drive on the energy, which is a function of mass, not volume. Professional fleet operators and informed drivers know this. They preferentially fuel early in the morning or late in the evening when ambient temperatures are lower. The fuel is cooler, denser, and you receive more energy per volumetric unit. This is not a myth, it's measurable physics. Some countries actually have regulations requiring temperature-compensated fuel dispensers to correct for this, but in many regions, including most of the United States, dispensers are not temperature-compensated. You're buying warm, expanded fuel on hot afternoons. The corrective action is to shift your refueling schedule. If your routine allows it, fuel your vehicle early in the morning before temperatures climb, or in the evening after the sun has set and the day's heat is dissipating. This simple scheduling change costs you nothing in effort but gives you measurably more fuel energy for the same price. It's a small efficiency gain, but over thousands of fill-ups across a vehicle's lifetime, it adds up to real savings and longer range per tank. It's the kind of detail that separates those who merely operate their vehicles from those who optimize every aspect of their operation. The eighth mistake is a failure to inspect and prepare the fueling environment itself before you even exit your vehicle. The error is this: you pull up to a pump, you get out immediately, and you begin fueling without taking 10 seconds to visually assess the pump, the nozzle, the ground, and your surroundings for hazards or contamination indicators. This lack of situational awareness can lead to fuel spills on your vehicle, contamination of your tank, or even personal safety risks. Start with the pump nozzle itself. Before you touch it, look at it. Is it dripping? Is there fresh gasoline on the nozzle tip or handle? If so, someone before you has either overfilled their tank or the nozzle's automatic shutoff mechanism is malfunctioning. If you grab this wet nozzle, you're transferring gasoline to your hands and clothing. When you then touch your vehicle's paint, you're depositing gasoline on the finish, which can degrade certain clear coats or paint types over time with repeated exposure. More critically, if the nozzle is dripping due to a mechanical fault, it may not shut off properly when your tank is full, leading to an overflow and spill. Inspect the ground around the pump. Is there a puddle or stain? Fresh gasoline on the ground indicates a recent spill, possibly from a leaking nozzle, a customer overfilling, or even an underground tank leak. If you park over a fresh puddle and then fuel, gasoline fumes will be rising directly around your vehicle. Your act of fueling will add more vapors. The concentration can become significant. While ignition is unlikely, it's an unnecessary risk. Additionally, fresh gasoline on the ground is a slip hazard and can transfer onto your shoes and then into your vehicle's interior. Check the pump's display and meter. Before you insert your payment method or lift the nozzle, make sure the pump is zeroed out. If the display shows a previous transaction's volume or price that hasn't been reset, the pump may be malfunctioning. You could be charged incorrectly. If the pump seems old, dirty, or poorly maintained, consider choosing a different pump or even a different station. Fuel quality and equipment maintenance often correlate. Look at the trash receptacle near the pump. If it's overflowing, or if there are used paper towels and spill-absorbent pads visible, it's a sign that spills are common at this location. This might indicate poor pump maintenance or a customer base that doesn't know how to fuel properly. Either way, it's a red flag. Assess the lighting if you're fueling at night. Poorly lit stations increase the risk of personal crime, but they also make it harder to see spills, hazards, or the condition of the pump equipment. If you don't feel safe, or if you can't clearly see what you're doing, go to a different station. Finally, check your vehicle's fuel door and the area around your filler neck before you open it. Is there dirt, mud, or debris on the fuel door? If you open it carelessly, that debris can fall into the filler neck and eventually into your tank. Wipe it clean with a cloth or paper towel before opening. This takes 5 seconds and prevents contamination. This entire pre-fueling inspection takes less than 15 seconds. It's a habit that demonstrates situational awareness and a proactive mindset. It prevents spills, contamination, and ensures you're using equipment that's in proper working order. It's what professionals do. The ninth mistake is related to a lack of understanding about fuel station logistics and timing. The error is this: you see a tanker truck actively delivering fuel to the station's underground storage tanks and you think, great, this is fresh fuel, I'll fill up now. In reality, you're about to pump the most contaminated fuel that station will dispense all week, and you're doing it voluntarily. Underground fuel storage tanks are large, holding thousands of gallons. Over time, despite filtration and best practices, a certain amount of sediment accumulates at the bottom of these tanks. This sediment is a mix of rust particles from the tank itself, silica dust, degraded fuel components, and potentially water that has entered through minor leaks or condensation. Under normal, steady dispensing conditions, this sediment layer remains settled at the very bottom, undisturbed. The fuel drawn by the station's pumps comes from an intake positioned slightly above this sediment bed. When a tanker truck delivers fresh fuel, it does so at extremely high flow rates, often hundreds of gallons per minute. This fuel enters the tank through a drop tube, creating massive turbulence. The incoming fuel agitates the entire volume of the tank, lifting and suspending the sediment that has been resting at the bottom for weeks or months. This creates a cloud of contaminated fuel throughout the tank. The settling process, where this sediment gradually falls back to the bottom, takes hours, typically 4 to 8 hours depending on the sediment density and the tank's baffling. If you fuel during or immediately after a delivery, you are drawing from this turbulent, sediment-rich mixture. Your vehicle's fuel filter will capture some of this material, but it will clog the filter much faster than normal. If the sediment is particularly fine or the filter is already partially clogged, some will pass through to your fuel injectors, causing wear and degraded spray patterns. Over time, this accelerates the need for costly fuel system cleaning or injector replacement. The corrective action requires timing awareness. If you pull into a station and you see a tanker truck actively offloading fuel, do not fuel there. Choose a different station. If you must use that specific station, ask the attendant what time the delivery occurred and wait at least 4 to 6 hours before returning. A useful heuristic is to favor high-volume stations on major roads. These stations turn over their fuel inventory quickly, meaning fuel sits in the tanks for shorter periods, reducing sediment accumulation. They're also more likely to have regular deliveries and proper maintenance. Avoid low-traffic stations on side roads where fuel can sit for weeks, allowing sediment to build up and water to accumulate through condensation. This knowledge transforms you from a passive consumer who fuels wherever is convenient to an informed operator who understands the supply chain and selects fueling locations strategically for fuel quality. We're approaching the final set of critical errors, and I want to ensure you're prepared to implement these protocols immediately. If this information is actionable for you, demonstrate that by engaging. Go to the comments and tell me which of these 9 mistakes you've been making regularly. Is it the afternoon fueling, running the tank to empty, topping off, not inspecting the pump? Be specific. Your honesty helps others and reinforces your own learning. And if you're finding genuine value in this level of technical depth, show it by liking this video and subscribing to the channel. This isn't casual content. This is professional-grade knowledge delivered for free. Your engagement supports the continuation of this work. Let's finish strong. The 10th and final pre-fueling mistake is one of chemical compatibility and additive timing. The error is this: you've purchased a fuel system cleaner or octane booster or other liquid additive, and you pour it into your tank immediately before refueling, expecting perfect mixing and optimal results. Instead, you're creating conditions for poor dispersion, wasted product, and potentially even damage to fuel system components due to localized high concentrations. Fuel additives, whether detergents, octane enhancers, or stabilizers, are formulated to work at specific dilution ratios within gasoline. A quality fuel injector cleaner, for example, might contain polyethylamine or polyisobutylene as active ingredients. These are powerful solvents designed to dissolve carbon deposits on intake valves and injector nozzles, but they're designed to work when properly diluted in 15 or 20 gallons of fuel, creating a mild, consistent cleaning action over an entire tank's usage. If you pour a concentrated dose of additive into a nearly empty tank and then immediately fill with gasoline, several problems arise. First, the initial fuel from the pump entering the tank may not create sufficient turbulence to fully mix the additive. You can end up with stratification, where the additive settles or remains concentrated in one area of the tank. The fuel pump may then draw a slug of highly concentrated additive solution, followed by untreated fuel, creating an inconsistent mixture reaching the engine. This inconsistency can cause rough running or trigger the check engine light if the mixture swings too rich or lean. Second, some additives are aggressive solvents. If they contact fuel system components like rubber hoses, seals, or the fuel pump's internal diaphragms in concentrated form before being diluted, they can cause swelling, degradation, or chemical attack on these materials. This is especially true for older vehicles with fuel system components not designed for modern ethanol or aggressive detergents. Third, there's the issue of waste. If you add the additive and then drive immediately to the gas station to refuel, you may have only used a small fraction of a gallon of the treated fuel before diluting the entire tank again. The additive's cleaning action hasn't had time to work through the fuel system. You're diluting it before it can be effective. The professional protocol for additive use is to add the product to a tank that already contains at least 1/4 to 1/2 tank of fuel. This provides immediate dilution into several gallons of fuel, ensuring mixing through the existing turbulence. After adding the additive, drive the vehicle normally for at least 20 to 30 miles before refueling. This allows the treated fuel to circulate through the entire fuel system, through the pump, the lines, the rail, and the injectors. The additive can begin its chemical work on deposits where they exist. Only after this initial treatment phase should you refuel, which will further dilute the mixture but allow continued cleaning action throughout the rest of the tank. Furthermore, choose additives wisely. Use products from reputable manufacturers that disclose their active ingredients and have independent testing data. Avoid generic gas station brands making outrageous claims. Look for additives that meet top-tier detergent standards or are recommended by automotive manufacturers. Use them at the recommended intervals, typically every 3,000 to 5,000 miles, not with every fill-up unless the product specifies that usage rate. More is not better. Proper dosing and timing are what matter. This disciplined approach to additive use ensures you're getting the maximum benefit from the product while protecting your fuel system from chemical stress. It's the difference between a well-maintained fuel system that runs clean for 200,000 miles and one that requires expensive cleaning or injector replacement at 100,000 miles. We have now traversed 10 distinct pre-fueling errors, each rooted in a misunderstanding of physics, chemistry, or engineering design. These are not trivial tips. These are the operational protocols that separate vehicles that suffer chronic fuel system issues and expensive repairs from vehicles that run flawlessly for decades. The knowledge you've gained in this session is the equivalent of a semester course in automotive fuel systems condensed into a practical, immediately actionable format. Implementing these practices requires discipline and a shift in mindset. You must stop viewing refueling as a mindless chore and start seeing it as a critical maintenance event. Every time you approach a gas station, you're making decisions that will impact your vehicle's performance, longevity, and your wallet. Running the tank to empty kills fuel pumps. Fueling during heat soak causes vapor lock. Topping off a nearly full tank resuspends sediment. Ignoring vehicle orientation leads to incomplete fills. Using the wrong octane wastes money or damages engines. Fueling in afternoon heat gives you less energy. Failing to inspect the pump risks contamination. Fueling during tanker deliveries guarantees dirty fuel. Improper additive use wastes money and can cause harm. Each of these mistakes is avoidable with knowledge and attention. Each corrective protocol costs you nothing but a few seconds of awareness and discipline. The cumulative effect of implementing all 10 protocols is a fuel system that operates as the engineers intended, delivering optimal performance, efficiency, and longevity. Now, I turn the responsibility over to you. Review this list. Identify your weakest areas. Commit to changing those habits starting with your very next refueling event. Which mistake have you been making most frequently? Is it running to empty, or is it fueling during heat soak, or perhaps you've never inspected a pump in your life? Write it in the comments. Your self-assessment is valuable, both for your own learning and for the community. If you found this deep dive to be genuinely valuable, demonstrate that value by engaging. Hit the like button if you haven't already. Subscribe and turn on notifications so you never miss this level of technical content. Share this video with someone who cares about their vehicle. Your engagement allows me to continue investing the hours required to research, validate, and present this information. Thank you for dedicating this time to mastering the details that most people ignore. This is how you take ownership of your vehicle's health. This is how you avoid being another statistic in the repair shop. Drive with knowledge, fuel with intention, and I'll see you in the next technical breakdown.